in section 5.2, we've talked about disks, volumes of rotations by disks, volumes of rotations by washers. Today, we're going to talk about volumes by cross-sections. And what I mean is when you have, like, you think about it this way, a shape on the wall, and a different shape is protruding from it, but it's only as big as that base. So here's some examples. If you notice, this is a little bit different. It's like a pyramid where each step is a square. This has squares sticking up from a curve. This one has squares sticking up from a triangle shape. This one has squares, or triangles, I'm sorry, sticking up from a shape on a graph. And as I do a couple of these, it'll make a little more sense. So let's go ahead and jump into that first example. So, x squared plus y squared equals 1. To graph that, solve it for y. You're going to find that y equals the square root of plus or minus 1 minus x squared. The plus portion of that equation gives you the top half of the circle. The negative portion of that equation gives you the bottom half of the circle. So that's how we end up with a whole circle of radius 1. If you're familiar with circles, you'll know that that's a circle centered at 0, 0 with a radius of 1. So, what we need to know about this is this distance is the square root of 1 minus x squared. It's going to come in handy. That's the distance. I didn't really draw that best, but that's the distance from the curve to the x-axis is 1, radical 1 minus x squared. Now, they want the cross sections from this square to be x-axis, perpendicular to the x-axis to be squares. So in other words, they're having squares stick up from this shape. This should be as long as wide as the should run from the top to the bottom, but squares are sticking out from here. So I'm going to draw another version of that. We've got our circle. It's kind of a 3D model, so it looks a little bit different. And we've got, for instance, a square here. And we could have a square here. We could have a square here. We could even have, a little square here. We would have squares solid across each of those lines. Now, we're adding up a bunch of squares, so we need to do the integral of the area of a square and the thickness of our squares, just like our rectangles we did in 5.1, and the thickness of our discs and washers is in terms of x, because we are perpendicular to the x-axis. And these are going to be stacked from this point to this point, meaning they're going to go from -1 to 1. Now the question is, what is the area of a square? Well, the area of a square is side squared. But if we talk about these squares, I'm going to draw one. We know that half of this square is radical 1 minus x squared. So all the way across for the side would be 2 times radical 1 minus x squared. But for this to be the area, we don't just need our side length. We need our side length squared. So we are left with the integral from -1 to 1 of 4 times 1 minus x squared. And we can simplify this. 4 minus 4x squared. We need to anti-derive because this is 4x minus 4/3 x cubed, and we're doing this from -1 to 1. And if we plug in the 1, we get 4 minus 4/3. If we plug in the -1, we get -4 plus 4/3. So 4 minus 4/3 plus 4 minus 4/3. And we end up with an answer of 5 1/3. And our label on that is volume, so just 5 1/3 units cubed. Now, we're going to do another example with a shape other than a square. Same function. This time the cross sections are semicircles with diameters on the plane of the base. So now we're talking about having a line here that forms a semicircle. Oh, that was really bad. That forms a semicircle, or one here that forms a semicircle, and they would be solid. Enough of them that this would be a solid. It would look a lot like half of a basketball, something along those lines. So we have our base circle, which looks a little oblong because we're going three-dimensional. And then we have some semicircles. That are sticking out from those shapes. Now let's talk about a semicircle for a second. Here's the shape. We know that we know the radius because of before when we talked about this being radical 1 minus x squared, the radius of this is going to be radical 1 minus x squared. Now, we're adding up a bunch of semicircles, so we're going to have to, again, still the same region, the area of a bunch of semicircles with x thickness. How do you find the area of a semicircle? Well, it's half a circle, so 1/2 pi r squared. And if we talk about r is radical 1 minus x squared. Now, to go on from here, your allowed to pull constants out front. I'm going to put the 1/2 pi out front. This is just going to become 1 minus x squared when we square the radical. And we end up with an integral of 1 minus x squared. So, if I derive that, I get x minus 1/3 x cubed. And this is all from -1 to 1. So, keep my 1/2 pi out front. I'm going to do 1 minus 1/3 minus -1 plus 1/3. That'll all be multiplied by the 1/2 pi out front. 1 minus 1/3 plus 1 minus 1/3. So end up with 2 minus 2/3, which means we've got 4/3 times 1/2 pi, or pi over 2. We end up with 4 pi over 6, which equals 2 pi over 3. And this is also going to be units cubed because it's volume. So, basic idea, find the region of the base, use it to find whatever parts you need on your protruding shape. So like circle, half a circle is 1/2 pi r squared, square is side squared, triangle 1/2 base times height. Anything you need to be able to find the areas of those little cross sections and use an integral to add up the area of all of them from left to right or top to bottom, whatever the case may be, depending on what axis we are perpendicular to.